Hello everyone. Thank you for joining us virtually for our Senior Design Expo presentation. My name is Juan Avila and I am the team lead for the IoT Environmental Sensors team. Today my team and I will be showing you what we were able to accomplish this year virtually. To start off, here on the agenda slide, you will see today's presentation broken down. As we go through the presentation, I will let my team members introduce themselves at the respective slides. Now, before my team and I can even start to explain what we did over the year, we need to take a step back and explain what IoT is. IoT, or Internet of Things, is a network of physical devices embedded with sensors or software to inter-exchange information over the Internet. IoT uses microcomputers and cloud computing to record these real-time changes over long distances. IoT technology allows us to also track more localized dangers such as, in-office fires, smoke, or flammable gases. For our purpose, our network of devices will be collecting environmental data. Now for the problem. Humanity's presence in nature has created changes in our environment, and these changes are significant and can possibly bring harm to its inhabitants. It is important to detect and monitor these changes pre-existing in nature as well as those created by man-made infrastructure, however insignificant those may be. Tracking these changes allows us to find trends and prevent potential dangers such as wildfires, hurricanes, and tornadoes. As the photo on the right shows, as a fire grows, so do the CO2 levels. By designing sensors to collect this environmental data and having the data accessible in our server, our sensors would potentially help prevent from these fires in any environment of spreading due to quick detection from the sensors themselves. Now the objective. When we first met in the fall, we decided to set some goals for our project. Our main goal was to design and create a forestation system that would do the following. First, it would be able to detect both indoor and outdoor environmental changes such as CO2 levels, ultraviolet levels, and many more. Secondly, our goal was to gather data from the stations and upload it to an AWS or Amazon Web Service server where we can display and analyze the data collected. And lastly, we want the system to be easily deployable by the user and have them be able to build on top of our existing infrastructure. So for example, if someone wanted to add another station or a set of sensors, they can add it to our network with ease. Now, I'll be passing it on to my colleague David.
Thank you, Juan. Hello, my name is David Hernandez. Our project's objective is to track potential environmental hazards and relay that information to clients and archive that data. From this objective, we have built a three-layer design. First, at the lowest layer, is the sensor station, which outputs the data based on the sensor and relays it to the second layer, called the central layer. The central layer, controlled by the Raspberry Pi, is tasked with obtaining the data to store in the last layer, called the server layer. Our server layer is cloud-based and allows for data storage archival. Therefore, as shown in the image on the right, we have used the PSoC microcontroller for the sensor layer to build three sensor stations that communicates with one central station. Our first station serves as a weather station for outdoor uses. The second station will be used to monitor weather readings for indoor uses. The third station will be for air quality and harmful gases. With our three stations built, the central station's Raspberry Pi will use the communication protocol LoRa to retrieve that data. Furthermore, with a simple Wi-Fi connection, the central station will be able to connect to the server layer using the Amazon Web Service AWS database to store the data provided. The IoT system we have built has enabled a foundation of scalability to add any additional sensor stations according to the client's needs and further expand the IoT system capabilities. Here is an overview of our sensors in their corresponding stations. Station 1, we have chose sensors for outdoor weather applications and being able to send the data using the LoRa communication protocol to the central station. This leads us to selecting sensor BME280. This sensor measures three weather features, the barometric pressure, humidity, and temperature, with great accuracy. Next, we chose the Si1145 Uv Sensor. This sensor is capable of measuring UV light and infrared light and using the data to obtain the UV index through the central station. Lastly, we chose the weather kit SEN Si1145 to measure real-time storm conditions. This sensor is composed of three parts: the rain gauge for rain intensity, the anemometer for wind speed, and the wind vane for wind direction. Shown at the right is a Station 2, which again uses the BME280 as the main component sensor to measure temperature, barometric pressure, and humidity for indoor areas such as residential and commercial. In addition, uses the buzzer alarm to help notify if the readings are too high or too low from the BME280 sensor. This buzzer can help notify facilities maintain a stable weather atmosphere by turning on air conditioning or heater systems for control. For Station 3, we selected sensors for measuring outdoor and indoor gases. In addition, sensors capable of sending their data to the central station and be able to use that data towards a warning system to detect whether gases are above safe levels. So we selected the air quality sensor, the PPD42NJ, due to measuring air particles as small as 1 micrometers, giving a broad range of gas detection. Second, we chose another air quality sensor called the SJ811. This sensor goes a step further than the 42NJ sensor by detecting hazardous gases such as carbon monoxide, volatile organic compound gases, and metal oxide gases. Lastly, we used the MK4 gas sensor to detect indoor gases such as methane gas. This sensor can detect methane gas up to 10,000 parts per million. I will now pass it on to my colleague Anthony.
Thank you, David. Hello, my name is Anthony Huynh, and I will be presenting the implementation of Station 1. Here you can see the first half of Station 1 that I worked on. We have the LCD screen and its I2C module, the real-time clock module, the UV light sensor, and the LoRa module. The real-time clock, the LCD screen, and UV light sensor are all wired together due to I2C communication, while the LoRa module is wired up with SPI communication. On this slide, we have the second half of Station 1, which was done by David. Here we have a BME280 sensor, the RTC clock module, the anemometer, the wind vane, and the rain gauge. The BME280 and the real-time clock are wired together due to I2C communication, while the rain gauge and anemometer are digital switch output sensors and each have their own ports which they are wired to. The wind vane is also wired separately due to being an analog sensor. Now going over the sensors and modules attached to our Station 1. We first had to find out what voltages that our modules worked at, and if they did not have a voltage regulator, then we would have to use an external voltage regulator and step down the voltage to 3.3 or whatever voltages that they needed. For Station 1, we didn't have any issues with voltage and only had different interfaces. For our I2C modules, we had to connect them all in parallel to our I2C ports on our PSoC 5. We can then communicate with them by using their unique 8-bit addresses. Then we had a LoRa module which is connected to our SPI ports. For the rain gauge and anemometer, we had to connect these to digital GPIO pins. We then had to use a module on PSoC called a counter to then accurately get the amount of times that the switches on these sensors get triggered. Then we used the triggered amount to calculate the values. While for the wind vane, we had to connect it to an analog pin and use an analog to digital converter to be able to read the voltage coming out of the sensor. Now we can talk about the connection diagram for Station 1. For Station 1, the wiring of the first 5 modules is I2C, and we have them connected in parallel to the SDA and SCL ports of PSoC 5, which can be seen by the I2C line. We then can call each module by using the unique 8-bit address it has to retrieve and send data to each module. Then we have the LoRa module, which is wired up to 4 ports separately, due to it being SPI, which can be represented by the blue SPI line. For the wind vane, we had to wire it up to an analog pin, and for the rain gauge and anemometer, we wired them to a separate digital pins. On this slide, we have the first half of our Station 1 working, where it shows the time and UV sensor outputs on the LCD screen. On the left side, you can see the real-time clock output on the LCD screen on the top half of it. And on the bottom half, you can see the UV light sensor working, which shows the 0.03, 264, and 265 Each of those are the UV light, visible light, and infrared. This is with a room that is not well lit. And then on the right side, when I shine a flashlight onto the UV sensor, you can see our UV sensor goes up to 0.26 for UV light, and our visible light goes to 306. Then we have the second half of Station 1's results. This was done over termite using UART, which is sending PSoC data to the computer to display the values. Here we can see the rain amount and the wind speed, which is being displayed and after it was being calculated. And then we can see the wind vane output, which is a voltage, and then we correlate that voltage to a wind direction. On the right side now, you can see the BME 280 sensors outputs, which are temperature, pressure, and humidity. And now I will be passing it on to my group member, Jeffrey.
Thank you, Anthony. My name is Jeffrey Espinoza, and I'll be covering our team's second sensor station. This image shows our second sensor station. Located at the bottom, we have the sensors for this station. From left to right, we have a BME 280 sensor, a real-time clock sensor, a FRAM sensor, a buzzer module, and lastly, the LoRa module. Station 2 is said to be located in an indoors environment and display two different sets of data. The first set of data is the data within the sensors of Station 2. The second set is the data that will be sent from the other stations 1 and 3 to this station via the central station using the LoRa module. Station 2 is composed of 6 sensors and a single microcontroller. This microcontroller is a PSoC 6 microcontroller. This controller offers over 40 general purpose input-output pins or GPIO pins and supports communication protocols like I2C, UART, SPI, I2S, and many more. The table shown in this slide lists all the sensors in this station along with the voltage ranges needed for operation, the sensor's worst case current consumption, and the sensor's interface method. In this station, the only actual sensor that collects environmental data is the BME 280 sensor that measures pressure, temperature, and humidity. The other sensors, including the buzzer module, will be used to alert someone in the event that the BME 280 sensor records high temperature readings or any unexpected changes in the sensor's other parameters. Just like the other stations, this station will also have an LCD screen to display sensor readings, a LoRa module to send the data to our central station, an FRAM sensor for backup data collection, and a real-time clock module. Here we have the connection diagram for this station. Even though we have multiple sensors, most require the I2C pins of the microcontroller. We can differentiate each sensor connected in SPI by its 8-bit address. The I2C connection is denoted by the red-colored wire. The LoRa module is the only sensor that uses SPI protocol. The SPI connection is denoted by the light blue-colored wire. Lastly, the buzzer module. It requires a PWM interface to create square waves at frequency ranges between 2 kHz and 5 kHz. And the PWM connection is denoted by a green wire. Lastly, I'll be going over some results for our Station 2. These results were collected over the termite application. In the left image, we see recorded readings from the BME 280 sensor. For testing purposes, we set the rate at which the BME records and prints data to every 5 seconds. We also programmed our station to display the time at which the data was recorded. In addition, in the right image, we have tested a scenario where I placed a lighter close to the BME 280 sensor to simulate a hot room and obtain high temperature readings. We also defined a temperature level to trigger the buzzer module to play a loud warning noise. This trigger temperature was set to 33 degrees Celsius or 91 degrees Fahrenheit. We can see that once the sensor reads high temperature readings above the trigger level, a new message appears that the sensor is reading high temperatures and the buzzer module is turned on. Lastly, some features that we were not able to test due to the COVID-19 and virtual learning restrictions was the transferring and receiving data from the central station using the LoRa modules. Thank you. I will now be passing it over to my teammate, Vincent.
Thank you, Jeffrey. Hello, my name is Vincent Oviedo, and I will be explaining the details of Station 3. First, we have the agreed upon required components. Station 3 is designated to be an indoor station. With this in mind, we selected 3 sensors that can detect harmful indoor and contained gases. Our Si1145 sensor detects carbon monoxide, metal oxide gases, and volatile organic compound gases. The MQ4 is designed to detect several combustible natural gases, such as methane, liquefied petroleum gas, and hydrogen gas. Finally, our PPD42NJ sensor is capable of detecting the concentration of dust particles in the air. This information needs to be displayed locally as well as stored in a cache in case of a communications issue. That would be our FRAM module, the lovely MB85RC256V. With our components finalized, we end up with a microcontroller, 3 sensors, a display, a communication device, RAM storage, and a 9-volt adapter for power. Once our components were finalized, we began the implementation. This means taking our components and designing a schematic. The schematic helps us track the pin assignment on our PSoC as well as the pins on our components, and allows us to verify there are no logistical errors prior to assembly. This actually happened to us around this time. The component CCS811 ended up being delivered to another teammate's housing instead of mine. We were able to work around this issue, as you'll see in the next few slides. Here are the assembled components for Station 3. They've been calibrated and running for several hours on the 9-volt adapter. In Figure 1, it may be noted, as mentioned, 2 components are not present. The CCS811 module and the LoRa module are both not present within this test station. These sensors were configured by other team members due to this project being designed under quarantine restrictions. Figure 2 shows a close-up of our LCD readout. The LCD shows all available detectable gases, and in theory, these readings would be sent out to our AWS servers via the LoRa module. This is our CCS811 sensor setup. This was set up by Juan Avila, who spoke earlier. He was the individual who received the sensors, and he was able to work around the setback and build a test bench, as seen as Figure 2, to work with his own PSoC microcontroller and display the module's readings on the LCD display, as seen in Figure 1. Next is the coding behind Station 3. Figure 1 shows the top design required by PSoC. Since PPD and MQ4 sensors operate on analog readouts, their components require a system timer and a signal amplifier within the PSoC. However, our CCS811 LCD screen and FRAM modules operate on the I2C communication bus and are all nested within the I2C master module on the top right. Figure 2 shows a small sample of the code. The MQ4 sensor in particular is capable of detecting several different types of gases on its own. The PSoC will get these values, derive the sensor's readings into each gas's appropriate concentration, and perform the necessary tasks before taking another reading. Those tasks being displaying on the LCD screen, relaying the information via the LoRa module, and storing these values within the FRAM storage. And next will be Akbar Rizvi on the AWS database implementation. Thank you. Thank you, Jeffrey. Hello, my name is Vincent Oviedo, and I will be explaining the details of Station 3. First, we have the agreed upon required components. Station 3 is designated to be an indoor station. With this in mind, we selected 3 sensors that can detect harmful indoor and contained gases. Our CCS811 sensor detects carbon monoxide, metal oxide gases, and volatile organic compound gases. The MQ4 is designed to detect several combustible natural gases, such as methane, liquefied petroleum gas, and hydrogen gas. Finally, our PPD42NJ sensor is capable of detecting the concentration of dust particles in the air. This information needs to be displayed locally as well as stored in a cache in case of a communications issue. That would be our FRAM module, the lovely MB85RC256V. With our components finalized, we end up with a microcontroller, 3 sensors, a display, a communication device, RAM storage, and a 9-volt adapter for power. Once our components were finalized, we began the implementation. This means taking our components and designing a schematic. The schematic helps us track the pin assignment on our PSoC as well as the pins on our components, and allows us to verify there are no logistical errors prior to assembly. This actually happened to us around this time. The component CCS811 ended up being delivered to another teammate's housing instead of mine. We were able to work around this issue, as you'll see in the next few slides. Here are the assembled components for Station 3. They've been calibrated and running for several hours on the 9-volt adapter. In Figure 1, it may be noted, as mentioned, 2 components are not present. The CCS811 module and the LoRa module are both not present within this test station. These sensors were configured by other team members due to this project being designed under quarantine restrictions. Figure 2 shows a close-up of our LCD readout. The LCD shows all available detectable gases, and in theory, these readings would be sent out to our AWS servers via the LoRa module. This is our CCS811 sensor setup. This was set up by Juan Avila, who spoke earlier. He was the individual who received the sensors, and he was able to work around the setback and build a test bench, as seen as Figure 2.
Thank you, Akbar. My name is Jose Rodriguez, and I will be speaking about the Raspberry Pi 4. Now, for the Raspberry Pi 4, there are many different languages that we could have used, but for our case, we used Python because there was already implementations used, and it was much easier to use for our purposes. We did use Visual Studio Code. Now, we could have started off the code or used another terminal. Even the Raspberry Pi itself, you could put it in the terminal itself. But we decided to use Visual Studio Code. It's a little bit cleaner, and we didn't have any problems getting any connections. Now, before we started making any connections to Internet of Things Core, we did need to configure. If you can see right here in the bottom left corner, these are configurations. Now, as you can see right here, we did need to create an endpoint. I'll explain later how we created the endpoint. We also needed to create certificates. So as you can see here, we have one of the root certificates, and then we have the private key, and then we have one other certificate that we obtained. And another thing that we had to do was install all these libraries in order to connect to Amazon Web Services. So you had to install libraries for Python, you had to install libraries for Internet of Things Core, for DynamoDB, there were so many libraries that we had before we could even begin to send information. Now for this slide, I'll be talking about the dataset notation that we were sending the data packets, the format. Now, because due to COVID, we weren't able to meet up with our teammates, and we weren't able to actually test our devices and see if it actually picks up the data packets. But what we were able to do was create data sets ourselves and send it to Amazon Web Services or Internet of Things Core. Now for this example, as you can see here, we have a test 1, test 2, test 3. Now each of these numbers represents the station, so in this case it'd be station 1, 2, and 3. Now we cannot send just any type of information. There's a specific format that you have to get it in order for Internet of Things Core to be able to store the data in DynamoDB. Now, one of the things would be the quotation marks. So the quotation marks here for time, velocity, that's detecting the variables. So this would be direction, would be wind direction, rain gauge, UAV, temperature. Also, another thing is that we didn't send the packets with the variable units. So if you can see here, we don't have kilometers per hour, or we don't have PM or AM. That's because we will include that in the printout itself. But when storing it in DynamoDB as a data set, we will just send the actual data, the actual number. Now, another thing is, due to this, since we only could send numerical values, the time we decided to go with military. So in this case, you can see it's 15.45, which stands for 3:45 p.m. And as you can see here in the bottom, it actually seems to be getting a nice printout. So for this, you have 3:45 p.m. You have your velocity, 3 kilometers per hour. Direction. Now, here's another thing. For direction, instead of using northeast, we decided to use degrees because we could send the actual numerical number. So that's another thing. As you can see here, direction 45, it'd be in degrees. Now, for sending data sets, we did use Node-RED for one particular purpose. When you're sending information from Python, the Raspberry Pi, up to Internet of Things Core for testing purposes, sometimes if you're missing like a certain characteristic, like the quotation marks, or a certain format that doesn't align with Amazon Web Services, it won't show up on the database. So we used Node-RED to assure that we're getting the data sets. So right here, we know it was received, but it probably just didn't print out in the database. Now, similar to Python, we did have to obtain the certificates and the endpoint in order to accomplish this. As you can see here, we have an example. So this is a MQTT test client. This is an Internet of Things core. This is the topic, station, any station. So like for the middle part, it would be like station 1, 2, 3. In this example, it's 1. And the data set. So the data was received. As you can see here, this is what we had in the previous slide. It was uploaded correctly. And as we spoke about before, the reason we're doing this, we have to create rules to detect this certain format. So if you miss like a specific characteristic, it won't get uploaded to DynamoDB, which is what we're going to talk about in the next slide. But as you can see here, it is successfully subscribing, and it should be published. Right here in this picture you can't see, but if you click on this little area here, it is being published. And when we create rules in Internet of Things Core, we do create rules where if it picks up a particular variable, it will store it. So once it's published, it should be publishing in the database, DynamoDB. Now for this slide, this is the Internet of Things Core website or location. So for this area, this little region right here, this is where we pull our topic and what variables are we going to have. So you can see the temperature, humidity, rain, and then we have actions. So we're going to insert all those variables into the database, the DynamoDB. This is just more of an illustration to get an idea of where it's located. But before any of this is possible, we do need to make a policy where we can actually allow the message to be sent. It's just an example, temperature sensor. It could be anything, but we just named it temperature sensor. But this is the endpoint, and this will allow any message to be delivered to Internet of Things Core. And next we will be talking about the database. Now, as I said before, we are using DynamoDB to save our data sets. Now, in the top, we have wx_data. Now, this was more of an example, and it was forcefully injected. Now, that was more of a method to see if we were able to secure a connection to Internet of Things Core and see if it was actually a printout. We actually published the data sets like forcefully, as in printing them out ourselves. Now the one on the top, the stations, this one we actually used Python and we created the code ourselves, filtered them, and actually got them published through the Raspberry Pi itself in the database. You can see that these numbers right here are actually the timestamps. And as you can see here in the center, these are the stations. So station 1, 2, and 3. and these are the data sets for that particular station. Now, if you were to click on one of these timestamps, it will lead you to this screen. You're given the timestamp, the station number, so if we were to be moving along, it'd be 1, 2, 3 for each data set. And it gives you each variable and the value itself. So humidity, and then the percentage of humidity, rain, and then the amount of millimeters, temperature, and then 76 degrees in Celsius. Now I would like to pass it over to my teammate Juan.
Thank you, Jose. Now we'll be moving on to the conclusion. Throughout this presentation, my team has shared a lot of great information about our project. Now let's do a quick and brief review. As a team, we were able to build and design 4 stations along with the database. These 4 stations and database are a wireless network of sensors created to collect both indoor and outdoor environmental data, such as CO2 levels and weather. Some issues that we had were limitations due to COVID and remote learning. Some of the implementations, such as LoRa/LoRaWAN that we introduced in the fall, we were unable to complete because we couldn't meet in person to test the modules. But moving forward, if a group would like to take over, they will be able to seamlessly add their module to our station. And also, with the way we designed our network, and something we talked about earlier, there will be no issue with adding more different sensors or even adding more stations to this entire network. Before we end, we'd like to thank our advisors, Erslin and Dr. Liu, for all their help throughout the year. And also thank you to Mike, Dr. Bachman, and all the faculty working to help us all start and finish our senior design projects. And once again, thank you.